This is going to be a video about electric potential. Now you might be thinking to yourself, wait a second, electric potential, didn't we just do that? I swore we just did electric potential, and we didn't. We did something very similar though. We did potential energy. Potential energy has units of joules, and it had this formula that looked like a KQQ over R. I related this back to gravity, where I said, think of this kind of like a GMM over R, but that one picked up a minus sign, right? And that was saying, we've got this planet that's sitting here, and at this location, I'm going to put some kind of a mass, and that's going to have its own potential energy because of where it is from the center of that planet. Now, if I put a different mass there, let's say double the mass, then I'm going to get double the potential energy. And if I put, I know it's being a little bit redundant, extra something, if I put triple the mass here, I'm going to get triple the potential energy. So everything at this location, everything at this distance r from the center of this planet, there is something that it has in common. And then if we take that something and we multiply it by the mass that we put at that location, the mass of an object, then we get potential energy. If we want to think of this even in a little bit simpler terms, if we want to think of this kind of like MGH, then there is a piece that's the same for all of these, and then there's a piece that depends on just the object. So this is object dependent, and this part is just location dependent. I'm going to do the same thing with electrostatics. Instead of a planet, I'm going to have an R, or I'm going to have a Q. I'm going to go out to some object. If I put a charged object here, it's going to have some amount of potential energy. If I put something with triple the charge here, it's going to have triple the potential energy. And then I did red for double. Let's do that one. Double the charge is double the potential energy. So there is, again, some kind of a quantity that's the same for all of these, that only depends on being a distance r from this charge. That is called our electric potential. So our electric potential is not quite potential energy. Electric potential is going to get units of joules per coulomb, so that when I multiply it by a charge, I can get back to potential energy. And it's going to be K times Q over R. It doesn't have little q in it at all. It just has the charge of what's kind of setting the stage. Electric potential gets usually a letter of a capital V, but electric potential is going to be used to find potential energy. Potential energy goes into problems that deal with kinetic energy. Kinetic energy deals with speed. And the worst part, a capital V and a lowercase v really look the same as each other. I've seen all kinds of versions of this. I've seen people who use a smiley face for electric field or electric potential, or a star. Whatever it is you use, just be sure that you can be consistent with it and know what it is you're talking about. I'm going to use a V and just stick an underline on it, and that's going to have to be enough. That's electric potential. It is also a scalar quantity. So if I have a particle here and a particle here, and I want the electric potential here, Q1, Q2, R1, R2, my electric potential is just going to be, I'm going to have a K Q1 over R1 plus a K Q2 over R2. If my Q is negative, then I have a negative potential, and that's not a big deal. That's completely fine. I'd like to do just a little bit more with this. if I have a positive charge sitting here, that charge is going to have things going on around it. At some distance r, I said I've got an electric potential. I can take that distance r in any direction, and I've got the same. And ultimately, I can make a circle around my charge, all at that same distance r, and it's all going to have the same electric potential. What that circle is then, this is called an equipotential curve. Physicists are not known for creative naming, and this is no exception. This is a curve where the electric potential is equal. Pretty straightforward. Now, this is if we're thinking in 2 dimensions. If we think in 3 dimensions and want to say we've got a charge sitting here, we can extend r out of the screen into the screen type of thing, and instead of making a circle, we'll make a sphere. Instead of making an equipotential curve, we will make an equipotential surface. Same idea. For a class that's not based in calculus, we're going to pretty much work in 2 dimensions, and that'll work fine. This is at some distance r, and I'm going to call that r1. If I go farther out, to some other curve, to some other distance, r2, I'm going to get something different. So over here, this first curve, I'm going to say is v1. This second curve is going to be at v2. This is a positive charge, so maybe my v1 works out to be, I don't know, 10 joules per coulomb. Maybe my v2 works out to be 5 joules per coulomb. Everywhere on this first line, I get 10 joules per coulomb. Everywhere on the second line, I get 5 joules per coulomb. If I stick a charge here of maybe 2 coulombs, then on this inner surface, I'm going to get a potential energy of Q times V1, so 2 coulombs times 10 joules per coulomb equals 20 joules. Out here, if I were out on that second surface with the same charge, Q times V2 would give me 2 coulombs times 5 joules per coulomb equals 10 joules. So it's a lower potential energy, and that makes sense because if I take this charge and put it here and let go, it's going to go shooting away from here. It's going to shoot actually directly away from here. And when it gets to this second curve, now it's not going to stop there, right? It's just going to cross right by. But when it's crossing past that second curve and waving and laughing, it now has a potential energy of 10 joules instead of 20, which means it has picked up. It's dropped 10 joules of potential energy, which means it has gained 10 joules of kinetic energy. If instead I were to make this thing move from here, and I grabbed it and moved it to this location, for this red line, the amount of work done by my electrostatic force is going to be 10 joules. It's moving in the direction that the electric setup wants to move. I don't have to do anything to get it to move that far. I have lost 10 joules of potential energy, so this thing has done 10 joules of work. Along the purple path, I have also, or the field has also done 10 joules of work because it starts at the same potential energy as the red. It ends at the same potential energy as the red. So the difference is the same, and I get a net work still of 10 joules net work. It's not going to travel this direction on its own. In that case, something is fighting it, but that's okay too. We can mess around with that. What I do see is that this thing, if I let go, wants to move directly away. This is also the direction that my electric field points, and it points necessarily perpendicular to these lines. You've seen these equipotential curves before. If you look at something like this, if you are going hiking and you see something that looks like this for an elevation map, if I were to look at this, I would say right here, somewhere over here, I'm probably standing at the top of a small mountain. As I move farther away from there, I'm moving downhill. So I'm moving from a higher potential to a lower potential that's moving downhill. If I had this kind of an elevation map, this kind of a contour map, and I were asked, where is a region that I might try to avoid if I were going to be moving up this mountain from the ground? I would say this looks like a good region to avoid. Why? Because in a very short amount of space, I'm gaining a lot of elevation. So maybe I'm only moving across a horizontal distance of, I don't know, 100 meters, but I'm going up from 200 to 600. I'm moving up 400 meters in a horizontal distance of maybe 100 meters. That's steep. If I were to plan out my path for coming up this thing, I might like something this way, because over a much bigger distance, I'm gaining the same elevation. Now, I had said my electric field points in the direction of the sharpest drop-off, so it's going to be perpendicular to these, and that's what's going to happen here too, right? If I drop an object, if I put a ball down or something, it's going to roll like this. If I put it in this spot, it's going to roll like this. If I put it here, like this. If I put it here, and maybe over here I get something that looks like that. I'm perpendicular to my contour lines every time, and if instead of contours I think electric potential or electric fields and electric potential, then I know what I'm doing with an equipotential map. That's it.